And I'll go back and check these PowerPoints to make sure they're up there, because it's going to, if we can't get our book to start off with, we're going to have to deal with these guys. So the p-n junction, what do you think of p-n junction? Well, we come in and we deliberately bond these things together. So what can you imagine right there when the P meets the N? We'll look at that. Two blocks of material, one is the N, one is the P. The N region has many free electrons, the P region has many free holes. The two materials are fused together. The point of contact between the two is called what? P-n junction, and this is amazing. This is what semiconductor works. This is what semiconductors work on. It works on p-n junctions, P material and N material. At the instant the junction forms, well, what happens is you got this P material is looking for electrons, right? You understand. The N material is looking for holes. As soon as we bond them together, the electrons are going to start jumping into the holes, and the holes are going to start filling with electrons. At the instant the junction is formed, some of the N electrons jump into the P region. The electrons recombine with the holes. This leaves holes in the N region. And now we got a mismatch, right? You understand? So an N material itself has no charge. As soon as we bond them, now all of a sudden we create ions, because now the holes and the electrons in the N material does not match, and the holes and the electrons in the P material don't match, right? You understand? We'll talk about what that causes. This leaves holes in the N. This causes the p-n junction to become. The p-n junction itself loses all majority carriers at the junction, right? Because they're happy, right? Okay. The area on both sides of the junction, so they'll become depleted of majority carriers. This is so where it forms, we refer to this as the wall. Depletion. Because we've lost our majority carriers. Everybody okay so far? Just at the junction. So this is what they're calling right here. But the problem is now we call it the depletion region because there's no majority carriers. But notice it picks up a what? A charge. Everybody okay? You can't get any. These guys actually generate a voltage, but the problem is they can't move any current. If we tried to get a load, if we tried to run a load off this potential, we couldn't do it. But we'll talk about that in a minute. The presence of positive and negative ions on opposite sides of the junction creates a barrier across a barrier voltage across the depletion region. And we call it what? The barrier voltage. Now on your data sheets, it's going to be called VF. So if we looked at data sheets on a diode, so what we're looking at is y'all heard of diodes before? That's what we're looking at. So if we looked at the data sheet on a diode, one of the ratings is the VF of the diode. This is the barrier voltage that's across that thing. There's the amount of voltage necessary to move electrons through the electric field formed by the p-n junction. Silicon, the barrier voltage is, and we don't use, for some reason, they don't use engineering notation when they specify this. So it's around 700 millivolts for silicon and around 300 millivolts for germanium. And it's approximately, because there's no way in the world they could make two exactly the same, right? You understand? So this is Rutherford. Some books you see teach 600 millivolts. We teach 700 millivolts. Are we okay so far? So we don't need to see this. Forward bias. So this is a term that we're going to use. So bias. Let's define bias. So it's not being against something or leaning towards something. in semiconductors, bias is always, this is a DC voltage. DC applied to a semiconductor. And we say semiconductor, but we know now it's a doped semiconductor, right? To control its conduction characteristics. So we pick up two terms. We pick up what we call forward bias. So what this is a voltage we're going to apply to cause current to flow through the junction. Then we're going to talk about reverse bias. This is a condition that prevents current flow through the junction. Everybody okay? And what you're going to do in this class, so in DC, in intro, you played around with resistors. What does a resistor do? What's the function of a resistor? It has one function in mind. Well, what we're going to do this is we're going to use a lot of resistors to set these bias voltages. So here you're actually going to see what the true use of a resistor is, besides for generating heat. So basically in DC, your resistor does one thing, right? It drops the voltage and generates heat. That's the work it does. In solid state, this is what they do. They set the watt. They set the bias on these things. Forward bias means current flow acts like so. We say when a p-n junction is forward biased. So we come over here. We got this p-n junction, and I'm gonna draw it as a square. And one side we got P, and the other side we got N. Everybody okay? Okay. So how would we forward bias this? Well, first of all, I'm going to come over here and I'm going to have to put a resistor in here, because if I don't, I'm going to burn things up. And then what I would do is, this is what's nice, is we come up here and I'm going to take a DC supply and I'm going to put the plus toward the P, and I'm going to take the negative and put it toward the N. Everybody okay? Now what we have in here at the barrier, we've got this little tiny voltage that looks like this. And for silicon, it's about 0.7 of a volt. So what happens if I was to come up here and I was to have less than 0.7 of a volt, as long as I don't exceed that thing, this guy don't work. But as soon as I exceed that barrier potential, then what the N's going to do is it's going to take those majority carriers, which is nothing but a bunch of electrons, and it's going to push those electrons toward the center. The positive material is going to take all those positive charges, which we say are holes, and it's going to do what? It's going to push them toward the center. When they hit the center, what are they going to do? They're going to recombine as fast as they're going to do it. So right at the center, they recombine. So now we have it forward biased, and this thing would conduct. And it would drop very little voltage. How much voltage would it drop? About 0.7 of a volt. If it's silicon. Now it varies. The more current flow you put through it, it goes up a little bit. The less you put through it, it goes down. So usually it starts conducting right around 5/6 of a volt. So 0.7 of a volt is a good approximation. Okay, so that would be forward bias, right? You understand? So to forward bias it, I'm going to put my positive potential toward the P and my negative potential toward the N. We don't connect them. If I connected it straight across, that diode would pop just like that. Because once it gets above 0.7 of a volt, that sucker acts like a closed switch and it would conduct wide open. So we're going to have to protect these things with some type of resistor, right? You understand? Everybody okay? So literally, if we measured this, and this was 10 volts, and I measured across the resistor, it would drop about 9.3 volts. And if I measure across the diode, it's going to drop about 700 millivolts, 0.7 volts. This is a series circuit. Kirchhoff's law says the sums of the voltage drops have to be equal, right? Everybody okay? This pushes electrons toward the junction. The positive terminal pushes the holes toward the junction, and when they hit, electrons are looking for holes. The holes are looking for electrons. They just combine. Your conductor's constantly pushing holes in on one side and electrons in on the other. Outside, it looks like electrons are flowing in one direction, right? Inside, it's either predominantly electrons or only. Okay, so this is an example of forward bias. Have to put a resistor in there, guys. Not unless you check this, and we can check this. I'll bring one over next class. And this is the way we check it. We use what we call an ohm meter, check it. A lot of people don't. How does our meter measure ohms? How does your meter measure ohms? Well, used to, but now what they do is they have a constant current source. On digital meters, they put a constant current source. So what happens on your digital meter, it outputs a current, like 1 milliamp. And what it does is that when you hook it up, it steps the voltage up until 1 milliamp flows. Then 1 milliamp flows, it says, okay, and then it convert 1 milliamp, the voltage would be exactly the same, and then they put the decimal point in the right place and they put ohms on the outside. So basically, your ohm meter is a power source. That's what it is. And that's why you can blow them up if you put them into a circuit and you force current back through a power source. That's bad, right? I'm saying. So originally, when we came out with these things, these digital meters could not check these things. Later on, though, they added a higher voltage scale that it would come in. So literally, we can take a meter. So just about all your meters, if you look at it, it's going to have one of your scales that looks like that. And this is the symbol of the diode. This is the symbol for the N. This is the symbol for the P. So I can literally take an ohm meter and set it on the diode scale. And I can come up here and I can put that across there, and it's going to measure about 0.7 volts if it's good. If it don't measure about 0.7 volts, it usually means it's bad. So our meters have what we call a diode scale. Used to, you couldn't check them with a digital multimeter because they didn't put out enough current or voltage to break over the junction. So if it's active and I measure across this with a voltmeter, then it's going to measure about 0.7 volts. Now notice I'm saying what? About 700. Because it's got to defeat that barrier voltage that's created by those ions before it lets current flow, right? So these things they'll get hot. Anytime you run current through a voltage, you create watts. So these things are going to have a power rating on them that if you exceed them, it's going to cause problems, right? And of course, you're going to see big diodes, which are designed to handle a lot of current. They use a lot of semiconductor, and you've got little small ones, which are very low current ratings. And we'll show y'all some actually diodes. And we'll let y'all check them with y'all's meters. So bring your meter in next class, and we'll let y'all look at how to check these things. Once electrons, we've already looked at forward bias, all right? So this is what's happening when we forward bias. Everybody okay? Pretty neat, huh? Now let's look what happens. The barrier potential, everybody understand that barrier potential? Are we okay there? So that's created by that barrier because we create ions right at the junction, right? Everybody okay? And we must overcome this barrier potential before it conducts. So this is basically the way it's set up. So there's some resistance. These guys drop a voltage, right? If they drop a voltage, they can get hot. 0.7 of a volt for germanium, about 0.3 of a volt for 0.7 of a volt for silicon, about 0.3 for watt germanium. This is told you how we can measure it. This is so what does reverse bias do? So let's look at this thing. What's going to happen when we reverse bias this thing? So what I'm going to do now is I'm going to put my resistor in there. We could take the resistor out now. And let's put the positive on this side. And what I'm going to do is now I'm going to put the P right here and the N right there. Oh, that's forward bias. Rich. So to reverse bias this thing, what I'm going to do is I'm going to put the N toward the P, and I'm going to put the negative of the pi toward the P, and I'm going to put the positive toward the N. Well, what's going to happen, what's these N's going to do, what's the N going to do? Well, it's going to start doing what? These guys got a lot of holes in here. It's going to start attracting the holes. So the holes are going to move right here. It's going to increase the size of the barrier. These plus, it's going to take those electrons and start sucking them out. It's going to increase the size of the barrier. You understand that? And the barrier voltage is what's determining. Now, how big the barrier voltage gets will be determined by the size of this right here. You can literally, we call it breakover, and breakover is bad. If you put enough voltage on there, they'll start conducting in the opposite direction. Now, if they start conducting in the opposite direction, it usually damages the device because they're dropping a lot of voltage and you're forcing current back through it. So one of the ratings that we have on a P-N junction is what we call breakover voltage, which is bad, right? So it means if I put one polarity on them, and what's the forward bias? I put the what? Put the negative toward the N and the positive toward the P. And these guys here act like a closed loop. If I reverse bias them, they act like an open switch. And this is electronically, guys. This is automatically. So what happened? So this is showing reverse bias. The depletion region widens until the potential across it matches the external voltage. When the diode is reverse bias, the depletion region acts like basically a small capacitor. Remember that DC resistance of a capacitor is extremely high. The internal capacitance is called the depletion region capacitance. We don't really need to know that in this class. But this is what's happened. So originally, when we reverse bias it, we have a conduction for a really short time. We just can't, not infinite. It's conduction for just a really short time, and then it stops. When it's reverse bias. When it's forward bias, it conducts. When it's reverse bias, it blocks. As long as you don't exceed the breakover voltage. We can cause anything to break over, right? You understand? Like when I go out and buy a water pipe, the walls are rated at a certain pressure. If you exceed that pressure, what could happen? You could bust, right? Right? You understand that? So a lot of times our pipes freeze and the water, ice starts expanding. It exceeds the pressure of the pipe, and what the pipe does, it busts. So if you break this thing over, if you put too much voltage across it, it will break over. And it will start conducting. And that conducting is going to be through a lot of voltage, and it's going to get hot, and it's going to burn it up just like that. So all your semiconductor devices are going to have what we call a breakover voltage. As long as you operate it below the breakover voltage, you're okay. If you operate it above the breakover voltage, then you could damage the device. Everybody understand that? So last thing, guys. So what's going to happen if I put AC on one of these things? So this is AC. And we'll talk about what this is made up of, but this is the way it figures. So this is positive and this is negative. I'm going to bring this in. I got to put a resistor right there. And then I'm going to come up here and let's put the diode in this direction right there. Let's move the resistor. I'm sorry. So the resistor would actually be the load. So we'll come over here and put our diode. So this is the symbol for a diode, right? And this bar represents the what? The N. The arrowhead represents the P. Everybody okay? And then I'm going to come over here and put a resistor, and then we'll hook it up to circuit common. Well, during the positive polarity, then this would be my AC source. This is an example of the AC source. And this is reference to common. So during the positive polarity, I'm going to put a positive on the P, a negative on the N. This guy would be forward biased. It would conduct, right? Okay. What it would do across my resistor, it would generate a pulse like this. That would be almost the same amplitude as this. It would be 7/10 of a volt less shorter because before it conducts, we had to exceed the 7/10 of a volt. Okay, during the negative polarity, this becomes negative, this becomes positive. The diode turns off. So I'd come over here and I'd get this guy right here, nothing. So what I would get across my resistor would be this right here. This is not AC anymore. This is what? DC. Now it's not good DC. We call it pulsating DC. We'll learn out later on how we can smooth it out. But what I've just did with a diode, and this is automatic. I mean, I could sit there on a switch and I could go back and forth and I could block the positive and pass the negatives, right? You understand that, or vice versa. But I would have to be able to switch that thing every 8.33 milliseconds. This guy does it automatically. We call this a half-wave rectifier, very easy to make. So a rectifier is a circuit that converts what? AC to DC. This is pulsating DC. I wouldn't put this on my stereo. It would hum a lot, right? You understand? But this is our first step from going from one. And this diode does it automatically. It does that switching. When it's forward, but when it's reverse bias, it cuts off. When it's forward bias, it cuts on. Off on, off on. And we can do this with AC. So AC automatically does what? Forward biases it and does what? Reverse bias. Later on, we're going to figure out how we can take this and convert it into this. How we can steer both the positive and the negatives to one side of the line. And then later on, we'll learn how we can filter this out and we can turn into this, which is still DC. It's still got noise on it, but it would be more. Then later on, we'll learn how we can regulate it and learn how we can make really DC, what we call regulated DC. And that's one of the first things we'll learn. Power supplies are very important. So by the time we get through with this, you should be able to build your own power supply. Not these guys. These are switching power supplies. We'll talk about the difference. We have two. One of them we call a linear power supply. One of them we call a switching power supply. The advantage of linear power supplies is they're pretty easy to design once you understand transformers and stuff like that. The nice thing about switching power supplies is they're very efficient and they're very small. But when this side here goes out, you can't fix it. So mostly when a switching power supply goes out, it's so complex that it's almost impossible to troubleshoot. So usually when a switching power supply goes bad, you just do what? Replace it. And that's why they encapsulate these things. If you open this up, it's going to be a big piece of epoxy in there. You can't even get to the power supply. You can't get to the diodes or anything. But I guarantee you there's diodes in here. I guarantee. Because no matter what type of power supply it is, one of the things we got to do right off the bat is convert what? AC into DC before we can even regulate. So these are switching power supplies. Linear power supplies, you can make, we'll give you all the information where you could build your own. Used to, you could buy all the parts from Radio Shack, but guess what? Radio Shack is no longer in existence. So everybody okay on the syllabus? Got any questions on the syllabus? So what's due before next class? The syllabus agreement, right? All your quizzes are due before Friday, midnight Friday. Everybody okay with that? And then, like I said, I'll try to check on the textbooks and see what's going on, because I don't think, I didn't check today, because man, today has been, yeah, I didn't check on that today, but I'll check on that and see what's going on with those, and see what we can do with that. So what we'll do next class is we'll finish up this chapter, make sure we understand this, and then we'll go into an introduction to AC. Because we can't understand power supplies until we understand AC, right? So if you had AC, you're a step ahead. If you ain't, it'll be a review. If you hadn't had AC, you'll be ready for AC next time you get into it. Please, What, Anthony? Please log off. Yes, make sure y'all log off these computers before y'all know how to do that, right? Make sure y'all log off. Because if you don't log off, we use the same password. If you use Blackboard open, then the next person log on can see your Blackboard stuff. Everybody understand that? Make sure y'all put them in the right slot.